Hi, everyone. My name is Allison Koyama, and I'm part of Hamamatsu's marketing group. We would like to thank you all for attending today and welcome you to our first in a series of photonics webinars. Today's topic is Introduction to Photodetectors Part 1, which is being presented by Slavomir Fiatek. Slavomir is a senior university lecturer of physics at NJIT. He is currently working with Hamamatsu as a scientist consultant, writing and lecturing on various photodetectors and emerging markets, such as SIPM, PMT, LiDAR, flow cytometry, and much more. Today, our runtime will be approximately 5 minutes. I'm going to be doing some housekeeping items, but in the meantime, you should see 2 multiple choice polling questions pop up on your screen. If you could fill those out while I talk, that would be great, and I'll just be closing them out when I'm done. Just some items to note. All of your devices are being muted and video is disabled. If you're having any connection issues, don't worry. We're going to be recording this and we will be emailing out a link to all the registrants once it's available. We won't be doing any live Q&A session at the end of the webinar, but you are welcome to ask questions in the Q&A box. If you just type in your question, please choose all panelists and then hit send. We'll try to answer as many of these questions as we can, but if we run out of time, we'll be sure to get you a reply by email. We're also going to be sending out a brief survey at the end, so please take a moment and let us know how we did. I'm going to be closing out the polling questions now and turning it over to Slavomir. Thank you. Slavomir?
Thank you, Allison. Thank you for a very nice introduction. And first of all, I would like to thank everyone for attending our series on photodetectors. Today's lecture, which will last about 45 to maybe up to 60 minutes the most, will deal with point detectors. This is part 1. On Thursday, we are going to continue this discussion with another 45 up to 60-minute presentation. Today's lecture is organized as follows. First, we are going to discuss some generic characteristics of photodetectors. After that, we'll spend some time discussing front-end electronics. The basic idea here is that photodetector without front-end electronics is basically useless. We'll finish today's presentation discussing some aspects of noise, electronic noise. On Thursday, we are going to discuss structure and operation of 4 point detectors. Shortly, I'll show you a gallery of these point detectors. Then we'll spend some time discussing applications of photodetectors, and we'll conclude part 2 again on Thursday with some comments about the process of photodetector selection. So even though I'm going to discuss a generic photodetector, please keep in mind these 4 detectors: photomultiplier tube on the left, photodiode, avalanche photodiode, and the silicon photomultiplier. So what is a photodetector? Broadly speaking, a photodetector is light-driven current source. What we see here is a generic photodetector which is illuminated by light with certain incident light power. Excuse me, we have some slight technical issues. So let me just, okay, we are now back. My apologies for that. Okay, so now without much ado, so what is a photodetector? As stated already, is a light-driven current source. What you see here is some generic photodetector, which is illuminated by, in this case, monochromatic light with some incident light power P sub 0. Since a photodetector is going to be a light-driven current source, we're going to terminate this photodetector with an ammeter, probably the most ideal termination. In response to light, current flows. Let's call this current a photocurrent. The photocurrent will be given then by a product of spectral sensitivity times the incident light power. Spectral sensitivity, which is symbolized here with letter sigma, is probably the most fundamental characteristic of any photodetector. It is a measure how a photodetector responds to light. A somewhat related concept is quantum efficiency, eta. One can show that spectral sensitivity and quantum efficiency are related by the equation at the bottom. The equation shows that if I know spectral sensitivity for a certain wavelength, then I know quantum efficiency. One way to think about quantum efficiency is that it is a probability that incident photon produces electrical signal, perhaps an electron or electron hole pair, that can be or is measured. A few comments about spectral sensitivity. As already said, it is the most fundamental optoelectronic characteristic of a photodetector. It can vary on a number of parameters, but probably the most important dependence is on the wavelength. It can also vary with temperature and bias voltage for some photodetectors. As already stated, quantum efficiency is the probability that incident photon is detected. The two are related, and manufacturers of photodetectors will provide some information on spectral sensitivity or quantum efficiency with empirical curves as shown on this slide. Thus, on the left, we see a chart of cathode radiance sensitivity as a function of wavelength. In addition, the dashed line shows the related curve for quantum efficiency. So what does it mean? It means that for this particular PMT, if I wanted to observe, let's say, light with the wavelength of 1000 nanometers, there will be no photocurrent produced. There is no sensitivity simply at that wavelength. One can see that the sensitivity varies, and for this particular PMT, the largest photocurrent for a given incident light power will be obtained at 400 nanometers. On the right-hand side, we see a corresponding plot of photosensitivity as a function of wavelength for a photodiode. In fact, every photodetector, no matter what its type or model number, will have such curve provided by the manufacturer. Let's now discuss the second aspect common to all photodetectors, and that is the presence of dark current. Suppose we take our generic photodetector and we put it into a black box. There is no light illuminating the photodetector. Nevertheless, a current would flow. This current is known as a dark current. Whether light is present or not, a dark current is going to flow. For some photodetectors, in particular a PMT, the presence of light can enhance some forms of dark current. You may be wondering, what is the main source of dark current? There are actually many sources, especially for PMT, but what's common to all photodetectors is thermal excitation of charge carriers. But again, there are other sources. In case of a PMT, there are about a dozen or so sources of dark current. So let's again look at some points relating to dark current. As already stated, there is going to be a flow of current regardless of the presence of light. The magnitude of this dark current will depend on many factors, such as temperature, such as the type of material that is photosensitive, whether it's a silicon or indium gallium arsenide or some particular type of photocathode in PMT. That will matter and will affect the magnitude of dark current. It may be a function of bias voltage, active gain, active area, and gain, and more parameters as well. There are, however, some situations in case, especially of photodiode, when one can operate a photodiode without the presence of dark current. However, this operation is not always favored since some trade-offs do exist. The presence of dark current will cause an offset in the output signal. We are going to learn in this presentation that that offset can be taken out, i.e. we can subtract it. However, what we cannot subtract is noise that dark current is going to contribute to the measurement. It is because of that noise that is certainly favorable to have as small dark current as possible. And that noise that dark current contributes is known as dark current shunt noise. Manufacturers typically provide some information on dark current in form of plots. What's plotted against what will depend which parameter is most relevant. Thus, on the left-hand side, you see a plot of anode dark current for a PMT as a function of temperature. What's done here is that we keep, for example, the biasing voltage constant, but we raise the temperature of the device, and one can see that dark current is going to increase actually quite rapidly on this log plot. On the right-hand side, we see a plot of dark current as a function of reverse voltage for a photodiode. Again, here we see an increase of dark current as the reverse voltage is increased. Let's look at the very important property of photodetector, which is gain. So at this point, let me state that 3 of our 4 photodetectors have gain, intrinsic gain. First, PMT, which can have a gain of million or so. Silicon photomultiplier is another photodetector with intrinsic gain, where gain can be comparable to that of a PMT. And then avalanche photodiode, which has also gain, but typically smaller, much smaller than those of SIPM and PMT, on the order of about 100 or so. Photodiode does not have gain. So what is gain? Well, again, let's go back to our generic photodetector. I shine light monochromatic with some incident light power P sub 0. We learned earlier in today's presentation that the photocurrent was given by sigma spectral sensitivity times incident light power. However, if the photodetector has gain, mu, then that photocurrent is going to be increased by the gain factor mu. So this is what we mean by intrinsic gain. Let's go through some points regarding gain in photodetectors. The point 1 was already stated, that 3 photodetectors, PMT, SIPM, and APD, have intrinsic gains. So what intrinsic gain does is to increase the magnitude of the photocurrent, but also it also increases the magnitude of some forms of dark current. Not all, but some are increased by the same factor or smaller. There are different gain mechanisms in our photodetectors. In case of a PMT, which we'll discuss in greater detail on Thursday, it is the secondary electron emission from diodes that is responsible for the gain mechanism. However, in case of silicon photomultiplier and APD, it is the impact ionization of electrons and holes that give rise to gain. And so point 5 is actually quite critical. So what can intrinsic gain of a photodetector do to us? The importance of that gain is that it can increase the overall detection signal to noise ratio. So please note that that overall improvement in signal to noise ratio cannot be achieved if I simply use an amplifier of gain mu. It is the intrinsic gain of the photodetector that will have this property of improving signal to noise ratio, not just a gain of an amplifier connected to a photodetector with a gain of 1. This is a very important distinction, important point to make. And so more about signal to noise ratio later in today's presentation. So which property or which characteristic affects the gain? And the answer is in almost all cases, the gain will be a function of the biasing voltage. It will either increase linearly with bias voltage, like in case of silicon photomultiplier, or it will increase as a power law in case of a PMT. Again, manufacturers are going to provide the relevant plots regarding the gain of a photodetector. And so thus, on left-hand side here, we see a plot of gain as a function of supply voltage for a PMT. Please take a note of the supply voltage. These are quite high in case of a PMT, hundreds, even thousand, and even more volts. And this upper solid line shows the resulting gain. And for this particular PMT, we see gains of about 10 to 4, 10 to 5, but that they can be higher, 10 to 6, 10 to 7, and even more. On the right-hand side, we see a plot of gain versus over voltage, which is effectively a function of bias voltage for a silicon photomultiplier. Here we see that the gain varies linearly with the bias voltage. Let us now discuss another property of a photodetector, which is terminal capacitance, and what that capacitance does to our detection. So again, we have our generic photodetector with a lead where current either flows out or in, depending on the detector. If I were now to measure capacitance between that lead, let's call it anode, and the ground, that capacitance would not be zero. It would be something. And that something capacitance is known as terminal capacitance. You may be wondering what contributes to this terminal capacitance. No, there is no simple answer. It depends on the photodetector. But for example, in case of a photodiode, this terminal capacitance would mostly be due to capacitance of the depletion region plus some parasitic capacitance of all the components from which the device is made. Whatever the reason, we do have capacitance. And important question to ask is what effect this capacitance has? Well, if we observe light in the DC mode, in other words, there is no intensity fluctuation, that capacitance is basically irrelevant. It does nothing. However, if the light comes to us with some modulation, i.e. we have AC light or pulse operation, then that capacitance is going to conduct current, i.e. it's going to participate in the formation of the output signal. The next effect of the capacitance is how its effect on the bandwidth, detection bandwidth. And we'll say more about this shortly in this presentation. Because of that effect on the bandwidth, the terminal capacitance will affect time characteristics of a photodetector, such as rise time and response time. Though not discussed in this presentation, terminal capacitance will also affect signal-to-noise ratio of the entire detection. And the reason for that is that it has an intricate relationship with the transimpedance amplifier that is commonly used to load or to terminate a photodetector. So capacitance has non-trivial effect on the noise of the detection. Terminal capacitance can be affected by a number of characteristics and properties. In case of photodiode and APD, bias voltage will affect the capacitance. For these detectors, photodiode, again, APD and SIPM, terminal capacitance will be a function of active area. In other words, larger the active area, larger the capacitance. It is very important to make now a point that this is not so for a PMT. In case of a PMT, the capacitance, terminal capacitance, is mostly due to capacitance between the anode and the last dynode, something that we'll talk about on Thursday. It does not depend on the active area. And so therefore here, this correlation does not exist. And that makes PMT sometimes a good choice where a bandwidth and large active area are important. Again, if relevant, doesn't have to be always relevant, but if for a given photodetector, terminal capacitance is a relevant quantity, again, manufacturers will provide information about terminal capacitance. So here we see a plot of terminal capacitance as a function of reverse voltage for some photodiode. We see that the capacitance decreases as we increase the reverse voltage. If you're wondering why this happens, that is because as we increase the reverse voltage, the depletion region increases in width, and then that reduces the capacitance or junction capacitance of that depletion region. If you're wondering what would happen if I were to keep increasing the voltage, well, at some point photodiode would not work properly. However, you could never drive terminal capacitance to zero because at some point you would see a contribution of parasitic capacitances. Everything has a capacitance. So wires, shields, etc., from which photodiode may be made of, will contribute capacitance to as well. So let us now spend some time discussing time characteristics of our generic photodetector. So here it is, and we are going to illuminate this photodetector with either a single photon, or if that's not possible, with a delta pulse. By delta pulse, I mean a pulse of light that has no width in time. And we're also going to assume that this illumination is uniform, which means the entire active area is uniformly illuminated. It doesn't have to be. There are many ways of doing this experiment, but in this discussion, let's just assume that that's the case. Probably the simplest way to think about it is just single photon. Okay, so we have a single photon or delta pulse, and that photon strikes the active area at t equal to 0. Now the question is, when will we see a response on the detection side? So this particular photodetector is terminated with the load resistance R sub L, which means that at some point in time, I should expect to see some voltage build up on this resistor. I also drew here terminal capacitance, which is again a part of the photodetector. The first point to note is that the response is not instantaneous. We have to wait some time until the signal appears on the resistor. And that signal is going to first increase with time, reach some peak value, and then decline. So we're going to get a pulse. The shape of this pulse will depend on the photodetector. In case of PMT, the pulse is quite symmetric, whereas in case of SIPM, it's quite asymmetric actually. So some nomenclature, the time elapsed from t equal to 0 to the moment of time when the pulse reaches the maximum value is known as response time or transit time. Now the time it takes for the pulse to go from 10% to 90% of the peak value, this time is known as rise time. Rise time is often crucial in various detection setups. Now, the signal now declines as the time it takes for the signal to decline from 90% of its value to 10% is known as fall time. Also sometimes important, but perhaps not as important as rise time. So please note that whether we have one photon or a delta pulse, in fact, I could say never, never say never, but here I can confidently say that you'll never get a delta function as a response. There'll be always some pulse with some width. What that width is will depend on a number of characteristics of the photodetector and on its state of biasing. Suppose I repeat this experiment many times. In other words, one photon at a time, and I obtain these pulses. And what I note is the transit time or the response time. If I did this experiment so many times, one thing I would find is that this transit time is not the same each time. In other words, it's going to show a spread or variation. Suppose I plot these transit times as shown here, then in most cases, one would get some sort of Gauss-like distribution of transit times. This Gaussian distribution has a width, sigma, and that sigma represents what we call a time jitter. This time jitter will depend again on number of characteristics, like biasing also depends actually on the number of photons that impinge on the photodetector, and also depends on the where actually photons strike the photodetector. So because of these variations, especially with the number of photons, it is customary to represent this plot for single photon illumination. So one has to be careful. If I see a plot of time jitter obtained with a single photon versus one obtained with, let's say, with 100 photon illumination, they are not comparable. We are comparing different things. Something to make a note of. This time jitter, I would say, is probably more important, more crucial time characteristic than transit time. Transit time can often be easily compensated for, but time jitter simply contributes to error in time measurement. There are some applications like LiDAR and PET where we measure distance using motion of light. And so time jitter will directly contribute to error made in distance measurement. Let's now discuss a bandwidth. So a discussion of bandwidth must include not only photodetector, but also front-end electronics, since both are going to determine or affect the overall bandwidth of the detection. Let's do an experiment. Suppose that I illuminate this photodetector with light such that its intensity or its power is going to be modulated from, let's say, DC, which means no modulation, to ever increasing frequency of modulation. On the output, I'm going to measure, say, voltage. And I will plot, say, voltage as a function of modulation frequency. If I had ideal photodetector without any bandwidth restriction, then that output voltage should not depend on frequency of modulation as long as average power is the same. However, again, such photodetector and photodetection system does not exist. Every single one will have some bandwidth limitation, which means that this voltage perhaps eventually will begin to decline as I increase the frequency of modulation. So in this particular presentation here, case, I'm showing you a case where we have a low pass. In other words, low frequencies are transmitted, but then the transmission declines as frequencies increase. So when the power drops to about half, not about, but half, then this width in frequency will be known as bandwidth, detection bandwidth of this system. If you're wondering what affects detection bandwidth, primarily the terminal capacitance, and in this case, the value of the load resistor. If either one increases, then the bandwidth is going to decrease. If instead of using a load resistor, I'm going to use, let's say, transimpedance amplifier, every amplifier, again, will have some frequency response. So the bottom line is not just photodetector, but also the type of front-end electronics I use that overall affect detection bandwidth. Let's now discuss dynamic range. Here is a plot of output versus input. So this output could be, I don't know, voltage, current, as a function of input, maybe a light power. If I had ideal detector, then there should be a linear relationship between output and input going from 0 to, let's say, infinity. But no photodetector is going to act like this. First, if I have very low light powers, the output will basically stay flat, and that's because of the dark current that the photodetector produces. Only when I increase the incident light power to levels high enough that the response starts to turn over and increase. And so this light power would be the lowest, more or less measurable light power. As I increase the light power, the response of the photodetector will eventually flatten and completely become flat and perhaps may even decline. This state is known as saturation. Some photodetectors are easy to saturate, like SIPM and PNT, and others are much harder to saturate, like photodiode, but they all saturate at certain level. Therefore, by dynamic range, I could mean the range of the measurable inputs light powers. By measurable, I mean measurement which will yield a signal to noise ratio greater than 1. So this concludes our discussion of some major photodetector characteristics. They're not complete. This is not a complete set. There are more, but these, I think, are the most fundamental to every photodetector. Again, I underscore the fact that this was a discussion of generic photodetector. On Thursday, we may make comments about specific photodetectors in regards to these characteristics. Let us now spend some time discussing types of front-end electronics that are used in conjunction to photodetector to make measurements. Since photodetector is, again, light-driven current source, probably the most ideal termination is an ammeter. You may be wondering why. Why is it ideal? It is ideal because ideal ammeter has zero resistance, which means that the potential at the anode is ground, and current sources love to be grounded. They don't like to be biased at the output. So this will be the most ideal termination from the point of view of photodetector. However, not necessarily the most ideal in practical use, since we often would like to not measure current, but actually measure voltage. You would like to convert current to voltage, and then that voltage will be manipulated for some additional purposes. So therefore, probably the easiest conversion of current to voltage is to use resistive termination. So I put the load resistor R sub L here between the anode and the ground. Therefore, the output voltage becomes current times RL. But this current I is the photocurrent, which is equal to sigma mu P0 times RL. Please note that if I were to increase RL, this resistor, the voltage would increase, and the current should not change because, again, photodetector is a current source. So this current should be the same regardless of the value of the resistor. This is true to some extent, but not always. If I increase RL too much, then the anode will become biased, or actually, once RL is different from 0, this point is no longer ground, but at potential V sub 0. However, if that V sub 0 becomes quote unquote too high, then photodetector begins to work it becomes to be biased and starts to exhibit nonlinearities and other adverse effects. So the point here is that one should be careful in choosing the value of the load resistor. It cannot be too high, though having high resistor is advantageous because, again, that increases the value of V sub 0. Another important point to make is that if you make this resistor too high, you are going to affect bandwidth as well. Since again, let's not forget that we have a terminal capacitance as well at the output. So an alternative, which is actually used quite often, is to use what's known as transimpedance amplifier. A transimpedance amplifier is an operational amplifier, op-amp, that has a feedback resistor, RF, and there's also a feedback capacitor. This capacitor is to improve stability of this amplifier. So what is the advantage here? The advantage is that because the way op-amp operates, this point right here is kept at the ground. So if the positive input is at the ground, this op-amp will do everything it can to make the potential on the negative input ground as well. Therefore, photodetector is quote-unquote happy because it is not biased. The anode is at the ground. We call such ground a virtual ground. And the output voltage almost looks like Ohm's law. It is Ohm's law actually, I times RF. And so one point to make is, could I make V sub 0 anything I want by increasing RF to anything I want? In theory, yes. In practice, no. There is a maximum voltage at the output that is allowed. For most transimpedance amplifier, that's about 10, 12 volts or so. Also, the value of RF will critically affect the bandwidth and noise performance of the amplifier. This is a topic that I will discuss in one of my presentations at later time, dealing with automotive LiDAR. So there are some trade-offs here as well at play. And before moving on, let's just make an obvious observation is that transimpedance amplifier is a circuit that needs to be powered, but it's much more expensive than a lowly resistor, which we discussed on the previous slide. Some operations of photodiode in this particular case will require an amplifier with very high input impedance. And so one can create such high input impedance amplifier using op-amp as shown on this slide as well. This is in the voltage follower configuration. In some situations, especially in scintillation-based observations, we would like to integrate a pulse, and so a charge integrator or charge amplifier can be employed. Typically, well, not typically, you would not want to use it in a DC or even AC operation. So this is something that is mostly used in pulse, where you have current pulses coming from a scintillator. And so this circuit integrates the current pulse, producing output voltage that is related to the input current pulse by the integral shown below. The purpose of this resistor is to allow the capacitor to discharge once integration has been performed. So let us now spend some time discussing noise, the various sources of noise. But first, let's start with the question, what is noise? What is signal actually? And so what you see here is a hypothetical output actually from a PMT showing two portions of the output when light is off and when light is on. So when light is off, we certainly see that there is some net current flowing, dark current, and there is this fuzziness around the dark current. That fuzziness represents the noise associated with the dark current. When light is on, then the curve, overall curve shifts, and we now see some current that is a superposition of dark current and the current due to light. Let's call it photocurrent or I sub P. However, please also note that when light is on, we still see fuzziness. And if you look carefully, there actually seems to be more fuzziness here when light is on than when light is off. Okay, so visually, you can clearly see the mean values, right? So that mean value will be the signal. And so this is the total signal right here, which includes, again, some average value of dark current and photocurrent. Let's call it IP sub D. This is the mean value of dark current. So if I subtract this IP plus D, I subtract from it dark current, I get IP. So this IP is our signal, which is again given by incident light power times sigma times gain. So that's the signal. What about noise? What contributes to this noise, to this fuzziness? Before moving on, just wanted to point out that on this slide, what we've done is to subtract indeed the effect of dark current. So that subtraction can always be done if it needs to be done. What we'll not be able to do is to somehow subtract this noise. But first, let's learn about some origins or sources of noise. Let's begin with multiplication noise. This is a noise that all photodetectors that have intrinsic gain are going to contribute. So suppose I have a part of photodetector where gain arises. At this point, it doesn't matter what it is. What I have here is some input, maybe some electrons or holes get injected into this region. So let's just think I have some input current. This input current has some input signal to noise ratio. Let's call it Sn in. Multiplication arises here, and therefore current now flows out after it's been amplified. And therefore this output current has some signal to noise out, Sn out. Might be tempted to think that Sn out is larger than Sn in, but actually that's not the case. Sn out will be always actually smaller than Sn in. In other words, the process of the gain has reduced the signal to noise ratio. But you may say, well, but didn't I say before that actually gain improves signal to noise ratio? Yes, the answer is yes, but of overall detection. Here, this is not overall detection. Here, we are just talking about Sn going in and out of a part of the photodetector where gain arises. Nevertheless, if I take the ratio of these signal to noises in and out, I get a number known as excess noise factor. And this excess noise factor is contribution to noise due to gain. And it's going to be multiplicative, as we'll see on the subsequent slides. Ideal photodetector would have f equal to 1. That would be a noiseless gain. However, that's never the case, and f will be larger than 1. Larger it is than 1, more noisy the gain is. Let's now discuss photon shot noise. Suppose I have a DC light impinging on the photodetector. And suppose that I have some super sensitive instrument to measure incident light power. And that super sensitive instrument would show me that even though I think I have DC light, there would be tiny fluctuations, maybe not so tiny, of the incident power. Those fluctuations represent noise already present in the incident light. This noise is known as photon shot noise, and it arises because of the random nature of producing light. Light had to be produced somewhere, and most likely came from a random process. And so that noise is going to be inherent to the light itself. That light then gets converted effectively into current. So we get our usual signal, but that noise that was present already with the light got embedded in the fluctuations of the current coming from the photodetector. One can show that the variance of that noise is given by the equation which I'm now outlining. And please note the important components. One is F, excess noise. That's why multiplicative noise, multiplication noise contributes multiplicative factor. And then we have mu squared, so that's gain squared. The square root of variance is what we call noise, and that's given by the equation below. So this represents what we call photon shot noise, always present. Similar argument can be made in case of dark current. Again, there is no such a thing as perfectly DC dark current. There are going to be fluctuations, and therefore dark current will also contribute noise, whose variance I'm now outlining with the mouse. So very similar equation as photon shot noise, where here ID represents the dark current at the anode. Another source of noise is the resistor itself. Suppose I have a resistor here, which is not biased. Suppose I connect its two legs with a wire. Because of thermal fluctuations, you could have tiny currents flowing back and forth with a mean value equal to 0. However, the noise around that 0, RMS value, will not be 0, and it's given by the equation below, known as Johnson noise, variance of the Johnson noise. Please note that it depends on temperature. Again, this noise is fundamental to a resistor. It doesn't matter how the resistor, can make ideal resistor from ideal materials, but this noise will be present because it comes from fundamental aspects of physics. So why did we spend this time discussing noises? Well, because now we are going to construct a figure of merit known as signal to noise ratio. And so this ratio, as every ratio, has a numerator, and the numerator has the signal. In our case, current. So this is the photocurrent. Downstairs, I have noises added in quadrature, and you will recognize the shot noise of the light itself. This PB represents the shot noise of the background light. Suppose I have an observation where we see both science light, but there's also background light. That background light would effectively act like, have an effect like dark current. We can subtract its mean value, but what we cannot do is to subtract off its variance. Then we have a noise to dark current, and here this is important. So this signal to noise equation is written for resistive termination. So if I've included the Johnson shot noise, Johnson noise of the resistive termination. Suppose that I have transimpedance amplifier. If that's the case, then this term would be the noise of the transimpedance amplifier. So looking at this equation, few points to note is that all the noises depend on B, which is the detection bandwidth. So if everything else is the same, but I vary detection bandwidth, so I make it larger and larger, please note that signal to noise ratio would decline. Another point that I will make on Thursday more strongly, there is a mu here. Suppose I divide numerator and denominator by mu. So this mu would go away, this mu squared would go away, but I would have mu squared here in this term. If that mu is large enough, this front-end electronic noise can be driven to non-importance. And so this will be, or this is, the importance of intrinsic gain. The intrinsic gain can make noise of detection electronics, in some cases, irrelevant. Some cases, you have to have enough gain for that. But please note that the penalty for the gain is the presence of this F. So larger F, larger overall this term is. Just before we close this presentation, just a few comments. The excess noise factor for typical PMT and SIPM is comparable, and it's about 1.1, 1.2. However, in case of APD, the excess noise factor, F, can be as large as 3, 3.5, and maybe even 4. So some photodetectors have, as I like to say, quiet gain, but others can have actually quite noisy gain. Excuse me. So before we close this presentation, one point to be made is that signal to noise ratio must be greater than 1 for detection to contain any useful information. In fact, when one sets up an experiment or optical setup, one needs to, the optimization process will be often conducted in such a way as to optimize or increase or have the highest possible value of the signal to noise ratio. And in this optimization process, the choice of the photodetector may be, or not maybe, is often a major part of the optimization. I'd like to thank everyone for listening to the first part. And if you are interested to know more about photodetectors, how they operate, I welcome you to our follow-up presentation on Thursday at the same time, 1 p.m. New Jersey time. So thank you again very much for listening. And before leaving, please take a note of our upcoming presentations here at Hamamatsu. Thank you very much.
Thank you, Slavomir, and thank you everybody for attending. If you would like a copy of the slides, I put my email address, akoyama@hamamatsu.com, in the chat box. And if you could just send me an email, I'll be happy to send you a copy of the presentation. Also, we're going to be having part 2 of this introduction to photodetectors on Thursday, the 28th at 1 p.m. Eastern time if you would like to join us. And we will just be sending out a quick survey with just a few questions to get your feedback on today. Again, we thank you all for coming.